We're going to be looking at rate of change. So just a review on domain. Domain is the x, or the input, and we're going to rename it the independent variable. Now when we say independent, we also have a dependent, and that would be your range or your output. So what's going to happen here to define independent and dependent in terms of a situation? We're going to start 60 meters away from the origin. Remember, the origin is located in this position, and walk at a rate of 10 meters per second toward the origin. So we're going to call our time the x, or the independent. It is independent. Who depends on it? Distance, or the y. The distance I'm at depends on how long I've been walking. So initially, time is 0, and I start at 60. So we're going to plot this ordered pair, 0, 60. So we're going to label our axes. The x is my independent, which is time. Y is my dependent, which is distance. Now we're going to need to scale this axes on y. Notice I can't go up to 60, so I'm going to refer to each one of these as a distance of 10 meters. So right here is where I'm 60 meters away from the origin. On the x-axis, each one of these lines is going to be referring to the amount of seconds. So if we try to fill in this table, after I've walked 1 second, I'm 50 meters away from the origin, or 10 meters closer. After 2 seconds, I'm another 10 closer. And after 3 seconds, again, I'm another 10 closer. So I keep decreasing. Now let's take a look at this picture. If I'm over at 1 second, I'm down at 50 meters away from the origin. At 2 seconds, 40, and at 3 seconds, 30. So we have this rate. The rate is 10 meters per second. We can visually see rate on my graph. And if I was to continue this, I would actually be even with the origin after 60 seconds. So we have this thing called a constant rate. And my constant rate we're going to refer to as negative 10 meters per second. It was negative because I was coming back toward. If you look at your line, the line is slanted downward. Let's try another situation. Again, I'm going to start 60 meters away from the origin. So the y-axis is my distance. The x-axis is my time. Time is my independent. We'll be labeling these every second. And we'll scale our y-axis again by 10. So this is 10 meters, 20 meters, and so forth. And once again, I start 60 meters away. And now my rate is 20 meters per second toward the origin. So after 1 second, I'm 20 meters closer to the origin. So I'm at 40. After 2 seconds, I'm another 20 meters closer. And after 3 seconds, I'm another 20, which means I'm even with the origin. Plotting these points, 1 second, I'm at 40. 2 seconds, I'm at 20. And 3 seconds, I'm at 0. Since my axes are scaled the same, if I compare the graph from the beginning function where I was moving at 10 meters per second versus 20 meters per second, you can see the change in the slant. The second graph is much more slanted than the first. So the rate of change is shown in that slant. So once again, it is a decrease at a constant rate. And the rate for this graph is I'm decreasing 20 meters per second. So my graph has a steeper slant to it than the first one. Let's try another situation. doesn't always have to be how fast you're moving. Your rate might be how much it's going to cost you. So my month and my cost, my month is going to be my x-axis, it's time, and my cost is going to be my y. Now if we sign up for internet, we have an activation fee of $30 and $10 per month. So when I begin my internet service, initially I must pay $30. Even though I haven't used it for a month, it needs to be activated. It costs me $30. After 1 month of use, I've paid the $30 and $10 more dollars, so now I've paid $40 total for 1 month of service. For 2 months of service, I've paid $50 total. So now this is my total cost. Over a 2-month period, I would have paid $50. After 3 months, I would have paid the $50 that I paid after 2 months in addition to $10 more dollars, which would have been $60. So notice the amount of money I owe is increasing. So we must scale our axes so we can graph and get a picture of this. We're going to label this months, so this would correspond to the number of months of service. And cost, well, we're going to scale this again by $10. So this would be $10, $20, $30, and so forth. So plotting these points that we've built in our table, 0, 30. So before I begin, I still must pay $30 for them to turn the switch and turn on my internet. After 1 month, I've paid $40. After 2 months, I've paid $50. And after 3 months, I paid $60. Again, notice I have a constant rate, and here my constant rate is $10 per month. It is positive because that's adding to my bill. Notice my line in this case goes upward. It's a line because it's a constant rate of change. It is always increasing. My fees are always increasing, where in the past with those walking situations my distance was decreasing. So here's a situation in a graph. Notice that my x-axis is time, my y-axis is distance, and if we take a look here, my domain then would be my x-axis, which would be time, and it is my independent variable. My range is the distance, which is my dependent variable. So a couple questions to ask here. I want a positive rate of change. Positive means that it is increasing. So where on this picture, this function, do I have an increasing segment? This line right here is increasing. So where I have a positive rate of change would be A. Where do I have a negative rate of change? Well, negative means decrease. So we look at the graph and find where it is decreasing, and it's decreasing here on segment C. So that has a negative rate of change. Now we have no rate of change at all in one segment here, and that obviously must be B. Why does that show no rate of change? Well, if you look at time here, time is between 3 and about 5 seconds here. 3 and 5 seconds. So time is moving on, but my distance hasn't changed. Notice my distance on this is always 6. It's constantly 6. I have not moved. I just stood there, and so that has no rate of change.